today's class we have to discuss the continuation of the first type of reactions of ethers. So here the reactions of unsymmetrical ethers we have to discuss. When an unsymmetrical ether reacts with concentrated hydriodic acid at high temperature to yield an alkyl iodide and an alcohol. So in previous case also, when we take dimethyl ether or diethyl ether, we are getting alkyl iodide and an alcohol, and that alcohol further reacts with the excess hydriodic acid, we get alkyl iodide. Okay, and the site of the cleavage depends on, here we are taking unsymmetrical ether. For example, in this case both sides are C2H5 groups, but in this case when we take unsymmetrical ether, if we take C3 group here, maybe different group here, maybe ethyl group or butyl group or some other groups can be there. Okay, so then the site of cleavage, carbon oxygen bond is cleaving in all reactions, so the site of cleavage of the carbon oxygen bond is different. So that's what it says, the site of cleavage depends on the nature of the alkyl groups. So what kind of alkyl groups are attached to the oxygen, depending on that the carbon oxygen bond cleaves. So let us discuss what are the conditions for this. When alkyl groups present in an ether are primary or secondary, can be either primary or secondary, it is the lower alkyl group that forms alkyl iodide. Lower alkyl group, for example, like, so if you have CH3 group here and C2H5 group here, CH3 group is the lower alkyl group compared to C2H5 ethyl group. So the lower alkyl group forms alkyl iodide. So lower alkyl group, CH3 group, is forming alkyl iodide, or the carbon of the lower alkyl group with oxygen gets cleaved. Okay, we will discuss the reaction and mechanism, because the mechanism involves the SN2 pathway and the nucleophile I- iodide attacks the least substituted carbon of the oxocation. Oxocation will be formed in the reaction, so we will discuss all this formed in the previous step. Okay, so when we look at the reaction scheme, you can easily understand the point. When methoxymethane, for example, we have taken methoxymethane or ethyl methyl ether, it is reacting with the hydriodic acid, concentrated HI, and then heated it, then we get iodomethane. So here the least alkyl group gets cleaved. Okay, so carbon oxygen bond of CH3O gets cleaved, and then this forms iodomethane, and this rest of this part will form ethanol, alcohol. So effectively we get two products. One is alkyl iodide or alkyl halide, and another one is an alcohol. Okay, and if an excess HI is used, the ethanol formed further reacts with HI to form iodoethane. So here if you use excess, if you want you can use, if you want to use excess HI, then ethanol will become ethyl iodide. Then we are getting a mixture of products in the reaction system itself. Okay, so one is iodomethane, another is iodoethane if you use excess HI. Otherwise ethanol we just need to remove it, then we get iodomethane. Okay, so let's discuss the mechanism. The mechanism starts with the protonation of the ether. As you know, ether oxygen contains 2 lone pair of electrons. This can be easily protonated in the presence of highly concentrated acid like hydriodic acid. So first step is the protonation reaction. So here the lone pair of electrons will abstract the hydrogen, and then it forms a protonated ether, or it is what is called oxocation. It is what is called oxocation, oxygen, positive charged oxygen. Okay, so this is CH3O plus H, CH2, CH3 plus I minus. Okay, so this is the iodide nucleophile. So here a nucleophile is generated in the first step after the protonation of the ether. And step 2 is an SN2 reaction. SN2 reaction means the nucleophile attacking the carbon from the backside, and then simultaneous formation and breaking and formation of the bond. The nucleophile I minus attacks the least substituted carbon. So it is more easy to attack the least substituted carbon, and thus carbon is more substituted, then the steric strain will be more, the steric hindrance will be more. Okay, and then it's not easy to attack the more substituted carbon. So the nucleophile I minus attacks the least substituted carbon of the oxocation and displaces an alcohol molecule by SN2 mechanism. Here the mechanism is very clearly written. Protonated ether, nucleophile is coming from the backside, attacks the least substituted carbon, and then the extended bond formation with iodine and this carbon, and the extended bond between carbon and oxygen, and extended bond between oxygen and this carbon. Okay, and then it forms finally or immediately it forms a methyl iodide, and then what remains is an ethanol. Okay, this is effectively is taking place here. Okay, and then further if you use extra amount of hydridic acid, then we get iodinate, then we get ethyl iodide or iodine. Okay, and the step 3 we just discuss when HI is in excess. That's what we were told in the last slide. And heating in continued, ethanol reacts with another molecule of HI and is converted to ethyl iodide. So here you can see that again ethanol, this is an alcohol. Oxygen is abstracting the hydrogen from this one, and then this is protonated, and or we call it as an oxocation, and again the attack of the nucleophile is taking place on this carbon atom, and then it forms an ethyl iodide and water. Okay, and in the other case when we discuss a more substituted alkyl group which forms an ether with a methoxy group. Okay, so when we consider one of the alkyl groups present in the ether is tertiary, so this is a group. Okay, tertiary butyl group, and it is a tertiary alkyl group that forms an alkyl iodide. Tertiary alkyl group that forms an alkyl iodide. Yeah, when we consider a tertiary group. Okay, in the previous case we were getting the least substituted carbon forms, alkyl group forms alkyl iodide. So when we use tertiary alkyl group as one of the substituent, then we get tertiary alkyl iodide. When 2-methyl, 2-methoxy, 2-methyl propane, 2-methoxy, so this is the ether we normally consider the most substituted alkyl is the parent compound. Okay, and then we have to give numbering this way 1 2. So this is 2, second carbon atom, a CH3 group is there, and also a CH3O group is there, methoxy group is there. So this is 2-methoxy and 2-methyl, and this is the 1 2 3. Okay, and this is the propane. Okay, so 2-methoxy, 2-methyl propane or tertiary butyl methyl ether is heated with concentrated hydridic acid, then we get 2-iodo 1 2. Likewise we can give the numbering 1 2 3, 2-iodo, 2-methyl propane, and methanol as formed. Okay, so when we use only primary alkyl group, then the least substituted unsymmetrical alkyl group, then we get least substituted alkyl group forms the alkyl iodide. But if we take tertiary alkyl group, then the tertiary alkyl group will form the tertiary alkyl iodide. Okay, so this is because in step 2, here the mechanism is different, we are going to discuss it. This is because in step 2 of the reaction, step 2 of the previous reaction was the attack of the nucleophile. Okay, and here also the step 2 of the reaction, the departure of the leaving group is a alcohol, creates a more stable carbocation. Okay, so the formation of the carbocation is actually an SN1 mechanism, and the reaction follows an SN1 mechanism. Okay, in the previous case it was an SN2 mechanism, and in this case it is an SN1 mechanism. In SN1 mechanism, a carbocation is formed, and more stable carbocation, nucleophile will attack the more stable carbocation, and that is the reason why we are getting tertiary alkyl iodide. Okay. So let us discuss the mechanism. The step 1, as we had seen previously, protonation of the ether is taking place, and then we get an oxocation. Okay, the lone pair of electron on this oxygen atom of the ether is picks up or abstract a proton from here and is getting protonated, and iodine will be left as iodide ion. Okay, so this is a protonated ether, and in the next step, it is a very slow step where it forms a carbocation. Okay, so here a carbocation is formed. So the leaving, this is leaving us methanol. Methanol is leaving from this one. Okay, so this bond will be broken in order to neutralize the charge. So this bond will be broken. Okay, and then we get an alcohol and a tertiary butyl carbocation. In tertiary butyl carbocation, the nucleophile is attacking from the front side, and then it forms tertiary butyl iodide. So this mechanism is SN1 mechanism. In the previous one, it was SN2 mechanism. That is the reason why in this case we are getting alkyl iodide of the most substituted alkyl group. Okay. So the reaction is when we talk up, the reaction is slightly different. Here also, when we use methanol with extra hydriodic acid, we can get methyl iodide. So then we are getting a mixture of compounds. Okay, if it is not necessary, we can avoid it. We have to use the exact amount of hydriodic acid. Then we will be end up with the tertiary butyl iodide, and methanol can be removed off. When an aryl ether is heated with concentrated hydriodic acid or hydrobromic acid, the cleavage of the carbon-oxygen bond occurs with the formation of phenol and an alkyl halide. Okay, so in this case, for example, we had given anisole as an example. Okay, anisole is heated with the concentrated hydriodic acid. The cleavage of the carbon-oxygen bond occurs with the formation of phenol. So here the alkyl oxygen bond, alkyl carbon oxygen bond gets cleaved. Okay, and then this forms the alkyl iodide. Okay, and then phenol. Okay, the cleavage of the carbon oxygen bond occurs with the formation of phenol and iodomethane. Okay, or methyl iodide. So here the reaction scheme is shown: anisole C3O C6H5 reacting with hydriodic acid. This bond gets cleaved, and then we get iodomethane CH3I and phenol C6H5OH. This is because in the methyl phenyl oxocation formed by the protonation of the ether in the first step, the OCH3 bond is weaker than OC6H5 bond because of the following reasons. So why alkyl halide is formed, alkyl iodide is formed, or alkyl bromide is formed when we take aryl ether? The major reasons are the carbon of the phenyl group is sp2. Phenyl group means benzene ring. Carbon is sp2 hybridized and hence more electronegative. Okay, so if it is more electronegative, this carbon oxygen bond is more, this carbon is more electronegative as compared to this carbon, because this is sp3 hybridized. Okay, and then the S character is increasing here, then it is more electronegative. Okay, if it is more electronegative, this bond is little shorter, or this bond will become more stronger. Okay, sp2 hybridized and hence more electronegative than sp3 hybridized carbon of the methyl group. Okay, and there is partial double bond character. So there are possibility for the resonance structures with oxygen and benzene ring. Partial double bond character for the oxygen phenyl bond due to the resonance. Okay, so this will become more stronger because of the resonance structures. And third reason, due to the steric effects, the attack of the iodide ion on the smaller group is favored than that of a larger phenyl group. Okay, so that because of on the ground of the steric hindrance, there are possibility for the attack of the nucleophile on the least substituted or the alkyl group is taking place. Okay, so there are three reasons. First reason is the hybridization. sp2 hybridized carbon of the phenyl ring is more electronegative, so the carbon oxygen bond is little lower and bond length is little lower and it is more stronger. Okay, as compared to the sp3 hybridized carbon of the alkyl group and the oxygen atom. And second reason is there are possibility for the resonance structures or resonance partial double bond formation between the oxygen of the either oxygen and the phenyl ring. And the third reason is steric effect. The nucleophile can easily come and attack least bulkier group present in the compound. Okay, so the reaction scheme is shown here. Anisole, in the first step, it gets hydrated, or the lone pair of electrons on the oxygen atom of anisole is abstracting the proton from hydriodic acid and gets protonated. We get an oxocation, and this oxocation further under the attack of a nucleophile on the CH3 group, then we get methyl iodide and phenol. Okay, and in this case aromatic alcohol is formed or phenol is formed. Phenol does not react further to give iodobenzene. Okay, in previous case whatever the alcohol is formed which further reacts with excess of hydriodic acid, it forms particular alkyl iodide. Okay, so in this case it does not undergo further reaction with the hydriodic acid to form iodobenzene because the sp2 hybridized carbon of phenol cannot undergo nucleophilic substitution reaction needed for conversion to the iodide. Okay, cannot undergo the conventional method. Phenol cannot undergo the conventional method of formation of iodine substitute when reacting with excess of hydriodic acid, because the strong bond between carbon oxygen of the phenol. Okay, so I am stopping here, so we will discuss the rest in the next class.